Hey, all you crazy cats and kittens. Sorry, I had to do it. Okay, so today we are going to go ahead and talk about what is called a logarithm. Super fun. A logarithm is going to take us one step forward in our mathematical journey where now you'll be able to solve equations where your variable is an exponent. Super cool. Okay, we're going to start off with a couple real life scenarios though, just so you can see when in real life would you actually need a logarithm. Okay, so we'll start off. First scenario, it says how many times would you have to double $1? Okay, so that means you have $1 and we're going to double it. Before you would have 8. All right, now this, yes, I know you can do it in your head pretty quickly, okay? Because if you have $1 and you double it one time, you would have $2, okay? So that's the first time. If you double it again, you would have $4. So that's the second time you doubled that $1. Now, if you double it again, hey, you hit your $8. So it would be the third time that you double, okay? But obviously not all scenarios are going to be quick like that where you can do it in your head. So what happens is you can go ahead and take a scenario like this and turn it into an equation. How much are you starting with? Well, we're starting with $1, okay? You want to double it. That's why the base is 2. If you wanted to triple, the base would be a 3. But we're doubling the amount, so it's 2 to the power of however many times you want to double equals 8. Now what happens is you can take 1 times 2 to the power of x. This is the multiplicative identity property. Remember when you multiply anything by a 1, it does not change its identity, okay? But in any sense, this we could go ahead and do in our head and see that, yeah, it's 3 times and we'd have $8. But what happens if it says how many times would you have to double that same $1 before you had 512? Well, yeah, you could figure it out. You could be like, all right, we're at 2, then 4, then 8, then 16, then 32, and you could keep going. But you guys, it's going to take quite a while to get to 512. So an easier way would be able to write an exponential equation. Remember what that means is your variable is an exponent. You're starting off with 1, okay? So that multiplicative identity, they just simplified 1 times 2 to the power of x just to 2 to the power of x because they multiplied by a 1. How many times did you have to double to get to 512? Well, we don't have a tool in our toolbox on how you can solve for a variable if it's an exponent. We know if you want to undo addition, you subtract. And if you want to undo multiplication, you divide. If you want to get rid of a power of 2, you have to take the square root. We have no tools that help us to solve for an exponent that is a variable. That's what a logarithm will allow us to do. A logarithm is an exponent in the sense that you can take any exponential function or equation and rewrite it as a logarithm without changing the value. So we can go ahead and rewrite the problem as a log, and that will help us to solve an exponential equation where our variable is an exponent. So let's go ahead and do this. A big majority of 7.3 is just practicing how you can write an exponential equation as a log and vice versa. It's just getting you used to the idea that these two things are equivalent of one another. They mean the exact same thing. They have the same value. So at any time, you can write a log as an exponential equation. You can write an exponential equation as a logarithmic equation without changing anything. It's just another way of looking at it. So thinking of that TED Talk you had, changing the perspective, that's exactly what this is, okay? One thing that you need to know, the base needs to stay the same, okay? So the base of an exponential function, in this case it's b, it's the value that has the exponent. Now when you have a logarithm, notice you have the letters log. That represents a logarithm. The little subscript, so it's a little number and it's lowered to the right of the letters log, this is the base of the log. The bases have to remain the same. Now the goal of a logarithm is to solve for an exponent. So when you write it in logarithmic form, whatever the exponent is, that's what the equation is equal to. Whatever your original solution was, that jumps over on the same side as a log. So again, bases stay the same. Whatever the exponent was, that's what the log is equal to because it's allowing you to solve for an exponent. Whatever your original solution is, and here they called it an a, it comes over on the same side as the log. It comes after the subscript, after the base, okay? So the first few I have done for you, when I printed out the notes For some reason, this little 3 was really, really light. So you might be able to see it in your notes. In mine, it was really barely there. So this is 3 to the power of 5, and it equals 243. Okay, so this is an exponential equation. If I want to write it in logarithmic form, I'm not solving anything, I'm not changing anything. It means the same thing, it's just another perspective on how you can look at this. Okay, so I want logarithmic form, so it's log. The base of the exponent is a 3, so the base of the log is a 3. So notice it's a little bit smaller and it's a little bit lower than the letters log. It's a subscript. That's where the base goes. Now your logarithm is equal to whatever the exponent is. My exponent was a 5, so the log is equal to a 5. Your original solution comes over on the same side as log. This is not a subscript. So notice the 3 is lower than both the log and the 243. So log base 3 of 243 equals 5. This means 3 to the power of 5 is 243. These two things mean the same thing. Okay, let's look at a couple more. 25 to the power of 1/2 equals 5. So if I'm writing in logarithmic form, you start off the letters log. The base is 25, so I have the base is 25. Whatever the exponent is, that's what it's equal to, so 1/2. And that is equal to a 5. So the 5 jumps over here. This means 5 to the 1/2 power, 25, the base. 25 to the 1/2 power equals 5. So if I picture this, 25 to the 1/2 power. Remember, when you have something to the 1/2 power, that means you're actually taking the square root because your index here would be at 2. The square root of 25 is a 5. So this checks. Let's look at the next one. I have 10 to the power of 4 equals 10,000. So this is log base 10. The base of the exponent is a 10, so the base of the log is a 10. It is equal to whatever the exponent is. So it's equal to the 4. The original solution, 10,000, comes over here. So log base 10 of 10,000 equals 4 is the same thing as saying 10 to the power of 4 equals 10,000. Okay, 2 more. Again, at this point, we are just practicing writing. 2/3 of your worksheet today, you guys, is just practicing this. Writing from exponential equations to logarithmic forms, then writing from logarithmic forms to exponential forms. Today is just a day to get familiar with what a logarithm is and how it works, okay? If I have 6 to the negative power of 1, it equals 1/6. So log, the base of the exponent is a 6, so the base of the log is a 6. The solution, which was 1/6, comes on over, equals whatever the exponent was. And keep in mind, we know the 6 to the negative power of 1, negative exponents means that it has to go on the bottom of a fraction. So all of these exponent properties that we have covered this year so far, you are going to see them a lot when we're working with logarithms. Last one, this time they use variables instead of numbers. Log, the base of the exponent is an a, so the base of the log is an a. Equals, it's always equal to whatever the exponent is, the c comes over here. So log base a of c equals b is the same thing as a to the power of b equals c. So this is the top third portion of your worksheet. You are just going to be given exponential equations, and they want you to go ahead and write them in logarithmic form. So at this point, you could already do 1/3 of the worksheet. Okay, now the next section on the worksheet, they're just having you go in reverse. They're going to give you logarithmic form. You are just rewriting what would it look like as an exponent, okay? Again, for some reason, this printed really, really light. This should be a 9. So it's a log base 9 of 9 equals 1. Sorry about that. I think the printer was running out of ink, okay? So if I am writing this as exponential equation, obviously I don't want the letters log, so I'm going to eliminate those. The base of the log is also the base of the exponent. So this is the 9. Whatever it was equal to, that's your exponent, and it has to equal the large number that was on the same side of the equation as the log. So 9 to the power of 1 equals 9. That checks. The nice thing is when you go from logarithmic form to exponential, you should be able to mathematically check and make sure that it works. Okay? If I'm going from logarithmic to exponential, I no longer want the letters log. The base of the log was a 2, so the base of the exponent was a 2. Whatever is equal to, that's your exponent, and it has to equal the large number that was with the log. So we can check it. 2 to the power of 9, oh, sorry, that's kind of There we go. 2 to the power of 9, yes, that is 512. So that checks. The next one, they gave us the logarithmic form. We wanted an exponential form, so you no longer want the letters log. The base of the log was an 8, so the base of the exponent is an 8. Whatever it's equal to, that is your exponent. So 8 to the power of 1, 3 has to equal 2. Well, to the power of 1, 3, remember that means it's a cubic root. The cubic root of 8 is 2 because it takes 3 2's to get to 8. 2 times 2 times 2 is 8, so this checks as well. Here's the next one. Log base 4 of 1 over 16 equals negative 2. The base is a 4, so the base of the exponent is a 4. The exponent is negative 2. You want to prove that it's 1 over 16. So 4 to the negative power of 2. Negative means that it has to go on the bottom. When it goes on the bottom, it's shown as a positive. 4 squared is 16, so it checks. Now again, you do not have to check these. The reason I'm doing this is because you're learning this for the first time, and I don't want you in the back of your mind to be thinking, what the heck is going on? So I am reviewing these different properties of exponents just as a way of checking, but also as a way of reviewing, so when this happens on the worksheet, you're not confused, okay? So don't worry about if you're thinking, I don't know how to check them. You don't have to. This is your answer right here. You are just rewriting. I am using this as an opportunity to review exponential properties with you, okay? Last one. Log, you don't want a log. We want exponential equation. Your base is a b, so the base of the exponent is a b. Equals whatever was on the right side of the equal sign, that's your exponent. So b to the power of 0 is 1. So here's another property, you guys. Anything to the power of 0 is a 1. That happens with logarithms too, because these two things have the same value. It's two different ways of writing it, okay? So it says a logarithm is an exponent. It's just an alternate way of writing it. It does not change the value of it. That means that the rules for exponents also apply, and that's what we saw here. Negative exponents go on the bottom. Okay, that was demonstrated here. The exponent was a negative, the value was on the bottom. If you have an exponent that is a fraction, so 1/2 or 1/3, that means a square root or a cubic root. Anything to the power of 0 is still a 1. Those things still hold, okay? So we're gonna go ahead and move to the final part. Now this is where they want you to start evaluating. Now this is the final part that you will see on your worksheet. I am gonna show you one more idea just because I think it's important for you to see what logarithms look like graphically. But as far as your worksheet, there's 3 sections if you look at it. The first section is being able to go from exponential functions or write it as an exponential equation, go ahead and write it as a logarithmic equation. Then the next section is just doing vice versa. They're going to give you the logarithmic equation, you go ahead and write it as an exponential equation. So the 2 ideas we've already done. Now the third idea, they want you to solve logarithms using mental math, okay? What exponent would you put on the base to get to this number? So we'll go ahead and review that. But first it's important that you understand what a common log is. It says a logarithm that has a base of 10 is called a common logarithm. So if no base is written for a logarithm, the base is assumed to be 10. So what happens is, because that's the common log, if your base is a 10, they will not always write it. So it says that the base is assumed to be 10 if no base is written. So if at any time you do not see the little subscript, you assume that it is a 10, okay? Now here it says evaluate log of 0.01. There is not a base, so that means it's an unwritten 10. It's a common log. So what you're doing is you are saying 10, because it's the base, to the what power gets you to 0.01. Now remember, way back in 7th grade is probably when you looked at bases of 10, when you first started looking at exponents. If I have 10 to the power of something, what that means is I'm starting with a 1, and the decimal follows the 1. How many times would I have to move that decimal? What would be the exponent to get to 0.01? Well, if I move it 1 time, the decimal would be here. I'd have to move it 2 times. I would be moving it to the left, so your value is -2. That's what x would be. What exponent could I put on the base, which is a 10, to get to 0.01? Okay, here's the next one. The base is 5. What exponent, you're evaluating, so you're trying to find the exponent, what exponent could I put on 5 to get to 125? Well, that's a 3 because 5 to the power 3 is 125. So this whole thing has a value of just 3. Here's the next one. There's not a written base, so that means that it is a 10. So 10 to the what power gets you to 0.1234. 1, 2, 3, 4 zeros and a 1. So again, if this is a base of 10, it means you're starting with a 1 and a decimal after. You're trying to figure out the exponent, which tells you how many times you have to move this decimal to get it to match here. So if I started after the 1, I'd have to go to the left 1, 2, 3, 4, 5 times. So the value would be negative 5. 10 to the power of negative 5 would get you to 0.00001. Last one. The base is 5. 5 to the what power equals 1 over 5. That's what you're trying to find. What is this value for x? Well, what happens is you want this 5 to go on the bottom. Well, in order to get your value on the bottom of a fraction, it means your exponent has to be negative. As again, that's those properties of exponents. But I want it to stay a 5. So it would be a negative 1. Because 5 to the power of negative 1, the negative would put it on the bottom. 5 to the power of 1 would keep it as a 5. At this point, that's everything that's covered in the worksheet. Okay, so the worksheet is just those 3 ideas: writing logarithmic equations, writing exponential equations, and then evaluating using mental math. Just being able to set up an equation so you could solve and figure out what the exponent would have to be. Okay. Now, I do think it's important for you to understand how logarithms work graphically as well. You do not have to do this on your assignment, but I do ask that you it's only going to take a couple minutes. Please continue to watch, do the notes with me, okay? Now, keep in mind, logarithms are inverses of exponents. Okay, so graphically, when we talked about exponential functions, remember we said that they are a curve shape. So here is a graph of y equals 2 to the power of x. That is an exponential function. It's demonstrating exponential growth because the base is bigger than a 1. Now, if logarithms are inverses, what that means is that when you graph the inverse, which would be log base 2 of x, because remember the bases have to match, it's a reflection over that line y equals x. So all that would happen is it would flip upside down, because remember all of your x's and your y's would just change. If I picked the ordered pairs used to create this curve, you would switch your x and your y, it would flip it. So looking at this, they are inverses. Inverses means you switch x's and y. Inverses mean the graph is a reflection over the line y equals x. Because an exponential function is a curve, when you reflect it, a logarithmic function is also a curve. So we're going to go ahead and just do 2 of these together. Again, they're not on your worksheet, but I do think it's important for you to be able to see how this works. Okay. So this is an exponential growth function because your base is 1.25. That is greater than 1. So I'm going to go ahead and do a table. So if I go 1.25 to the power of negative 2, let's round these to the 10th. So 0.64, I'm going to go 0.6. Up arrow, I want to change the exponent from a negative 2 to a negative 1. Round it to the 10th, oh, perfect, 0.8. Up arrow, I want my exponent now to be a 0. Anything to the power of 0 is 1. Up arrow, I want it to a power of 1. If I round it to the 10th, 1.25 would go to 1.3. Last one, if I put it to the power of 2, 1.56. If I round it to the 10th, I would have 1.6. So this is the graph of an exponential function. So let's go ahead and graph it. I'm just going to go 2, 2, 2, 2. So this is 2, this is 2, this is negative 2, this is negative 2. So when I go to graph this, I go to the left 2 and I go up 0.6. Okay, so I'm going to go a little bit more than a half. Left 1 up 0.8, 0, oh, I hit that 1. 1, I go up 1.3. At 2, I go up 1.6. So you can see, yes, it is curving. It's going upwards a little bit as you go to the right. Your domain. Notice the x values. All of them are covered. You're going to the left, you're going to the right, you hit 0. So your domain is all reals. Your range, your y values, notice that everything stayed above the x-axis. All of your y values are positive. So y is greater than 0. Okay, now if I know that this is an exponential function, right? Here is its inverse. log base 1.25 of x. This is an inverse. I do not have to try to calculate this again because we know that inverses just means you switch x and y. So 0.6, negative 2, you just flip them. Negative 1, 0.8 becomes 0.8, negative 1. 0, 1 becomes 1, 0. 1 and 1.3 becomes 1.3 and 1. 2 and 1.6 becomes 1.6 and 2. So now when I graph them, I should see that I still get a curve and I should get a reflection over that line y equals x. So if I go to the right a little bit more than half, I'm going down 2. If I go to the right almost 1, I'm going down 1. 1, it hits 0. 1 and a little bit, oh, I hit 1. If I go to the right almost to the 2, I'm going up 2 here. So check this out. Yes, I did get a curve-shaped graph. If I go ahead and I visualize this line, y equals x, yeah, we totally got a reflection. Yes, my lines are not very straight, but you can totally see that these are a reflection of one another. The domain, if I look at the domain of just the inverse graph, this graph stayed only to the right side. It only stayed in quadrants 1 and 4. So my x values were always greater than 0. I never went to the left side of the graph. If I look at the range, the y values, I'm below the x-axis, so I have negative y values. I have 0 for y values, and I have positive y values. So your range ended up being all real values. So the same properties as when we first talked about inverses. We graph this. When you graph the inverse, it's a reflection. To find your inverses, you switch x and y. Because you're switching x and y, your domain and range switch. In your original function, the domain was all reals. In the inverse, it's the range. In the original function, the range said you had to be greater than 0. In the inverse function, it was the domain. Okay, so the next one, I'm just going to kind of walk you through how you would do it. Just graphically, I want you to see how it's all tied together. If you end up with something like this, 3 over 4, I know a lot of you do not like to deal with fractions. If you have a nice fraction like 3 over 4, and you want to go 0.75 to the power of x, I would be totally fine with that, okay? So don't worry about it. There are two equivalent things. And then I'm just going to kind of show you in my notes what this would look like. Okay, so if I went ahead and I graphed it again, I said you can do 0.75, okay? So I went ahead and I found the ordered pairs and I graphed it. We found that the domain, this was exponential decay because 0.75 is less than 1. So as I went from left to right, that's why the graph curved downwards. I found my ordered pairs. Your domain was all reals because it was left, 0, and right. So it was negatives, positives, and 0. The graph stayed above the x-axis, so the y value was greater than 0. Then I just switched all of the x's and the y's, and when I graphed, I got this curve. It is still a reflection over this line, even though they crossed at that point, because you could flip this over, okay? It doesn't have to be two separate things like right there. It's okay if they intersect, as long as they still flip over the line. So I went ahead, flipped all of the x's and the y's, graphed it. The domain, your x values were always positive because this curve stayed on the right. So your x's were greater than 0, which was the same as the range for the original. My range, though, the y values, it's negative, 0, and positive, so it could be anything. So just like the domain was all reals here, the range was all reals. So graphically, I think it's important for you to see that it is all connected and how it fits. But to save you time, that's why I thought if I just do one with you and then show you what the other one would look like. Okay, now logarithms in real life, there are a lot of scenarios. I'm so excited to get to the second part of 7.4 because we talk about earthquakes and Richter scale readings and stuff. Very cool, okay? But one thing that we can already do is we can calculate what's called the pH level of foods. Okay, so the pH level, what it does is it represents the acidity in foods or in beverages. Here is what the formula is. To calculate the pH, it's a negative log. It's a base of 10. There is a log button on your calculator. It's right underneath the second key. This is a log. Notice it doesn't let you have a base other than 10. So you can only use this if you have a base of 10. But we can hit negative log, and then what you're doing is you're doing the hydrogen ion concentration for a food item. And so we're going to go ahead and calculate the pH level of milk, tomatoes, and lemon juice. So if I want to know the pH level for milk, it's negative log 0.0 0.00000025. And I did kind of separate that a little bit to make sure that I knew how many zeros. We're looking at 6 zeros here. So on your calculator, you guys, here is how you calculate the pH level of foods. Negative log 0.12345625. Close the parentheses because it opened one. You always want to close it. The pH level is 6.6. Okay, now what happens is a lower pH level means that there's more acid. So if we want to compare milk and tomatoes, we want to look and see which one has the lower. A lower pH means more acid. So if I'm looking at tomatoes now, negative log 0.00000316. So again, this is just a calculator, but it's cool because it's real life. So negative log 0.00000316. The pH level for tomatoes is 4.5. So because this is a smaller pH than milk, this tells us that tomatoes have more acid than milk does. This would be important for somebody who maybe has an ulcer or some type of medical thing where they have to limit the amount of acid that they end up eating or drinking, okay? Let's go ahead and look at the last one, lemon juice. Negative log of 0.0063. What do you think is going to happen? Say it out loud. Which one do you think is going to have the most acid? Okay, let's check it out. See if you're right. Negative log of 0.0063. Oh, 2.2. So this would probably be a really big no-no for somebody who had like stomach ulcers. That acid in lemon juice, oh my gosh, it would be so painful. So real life scenario, people who are maybe dietitians, work in a nursing home, that sort of thing, they may have to monitor the pH level for certain foods and beverages for some patients, some clients, that sort of thing. So you just use logarithms to figure out a real life situation. Today you just have a worksheet. It just covers the very basics of logarithms. Tomorrow we'll go ahead and look at some properties. I hope you're having a great day and I will talk to you soon, guys. Bye.